That in our
Hold
syllabus.
on a minute.
Hold on there, sir. But I know about that.
That in our syllabus, sir. That in our module.
Is a elective.
Good luck with them, man.
What do you mean good luck with them, man?
Hold on there, sir. Which module that? Because I not see that for the diet.
Check elective section.
Me have a semester too.
I see that on the elective. Sir, I don't know about that one there, sir. I see that now.
On the electives.
But you know, I say, some man I complain, say they don't get no grade and all, and sit down, I look for the grade, and the man them get all A. What I tell you?
Oh, yeah, sir.
So you need that thing then going with, man. Where they come from? Sure. But I'll open my gate. I don't know if it's set down again. So I'm going to send out the test tonight, the assignment tonight. So I'm going to turn it in by Tuesday.
Tuesday?
Yeah.
Hold on. Sir, we couldn't get it on the Thursday.
Finally Tuesday, sir.
Next week, Tuesday, on our final?
Yes, sir.
Yeah. Couldn't get the Thursday, sir.
All right. I don't work with you in a dream, man. I work with you. Thursday, 17th Thursday. How much people are there now?
15. 14.
So no set the date for date and time for the final. I make me know now before we start this.
Listen, I'm magnetics too, by that.
Maybe I not. A semester one. Next semester one. So usually a semester two in electromagnetics to come out. So exam when? The 9th or the 10th? Tell me.
The 9th, sir.
9th can work, sir.
Check here that cry, baby, them in the man.
Sir, when the man them come, in the class, we discuss back.
What time for the 9th now?
The 9th seems appropriate.
What time?
More like the afternoon.
That's very specific here.
Morning sound better, I want Sunday. 10 a.m., 11 a.m. Hello.
Make it the afternoon exam, man. Some man have to go to church on Sunday.
Yeah, a couple man go to church.
You know something? I don't really want conflict with nobody class. I prefer if I take it the 10th year, sir.
Sir, I did tell them, sir, you don't conflict, you know.
Yeah, nobody have fast on weekend.
I don't want to hear nothing about the church thing and whatever. I don't want no more problem.
All right, sir. Give me 2 times. One for the AM and one for the afternoon. I put it out in our group and ask.
So Monday the 10th, 10 to 12, or Monday the 10th.
Yeah, I may have match test for Monday, you know.
Sir, not the Monday, the Sunday, sir, the 9th.
Yeah, the Sunday, sir. Sunday afternoon.
10 to 12 or what time, I say?
Sunday at 1 p.m.
Jano, Sunday. Jano.
You hear that now?
them I forgot those.
You hear that? Man?
I forgot
Me
just
nah
work.
work with no Sunday, sir. No Sunday. Work with Saturday. Since we don't have no 7-day night class, work with Saturday or Monday.
So you feel there.
All right.
Yeah.
The 7-day man them, yo.
One thing, Friday.
On Sunday, man, we skip team church, you know. You see
Yo,
me?
Corey, you start them, man. Just work with the Sunday
One
program,
thing,
bro.
Friday.
Work with the Friday or the Monday.
And the Friday, the Saturday man, I'm gonna tell you them can't do work after sunset.
Well,
What's your?
I know
Night example.
Here we do, sir. Come we work with the Sunday, 1 o'clock.
It's 7.
Sunday is a neutral time for everybody.
1
Most people
o'clock.
don't have no work, most people don't have no class, and the afternoon free. Most people
I cook them
church
Sunday, I can
go in
cook
the
them
morning.
Sunday and do the test.
I can't cook. I go cook and go church Sunday. I not do no Sunday.
Say we work with the Sunday, right?
Sir, the test will be a multiple choice.
Eh?
It will be multiple choice.
I'm gonna make it difficult this time, you know, because I want to fight against I and I.
Sir, no, sir, no fight against you, no fight against you. No, sir, nobody didn't fight against you, sir.
I take care of I want to fight against I and I.
Sir, just
So you fight it, you know.
Sir, how when I get the other assignment there?
today we are get it, brother.
I
It's
said
early
it
next week, Thursday.
I'll get it today. I'll set eternity next week. So what? I'm not here yet to us. I'm right down, you know. Tell me.
Sir,
Friday.
hold on, sir. At the end of the class, we discuss this because everyone is not here yet.
All right, we soon do the syllabus, you know. So we are start today by talking about magnetic boundary condition. Who can tell me what the electrostatic boundary conditions were? What they were?
What the what, sir?
What were the electrostatic boundary conditions?
They were the tangential and normally I thought what, sir?
Yeah, man. What were they? E tangential one equal what?
Yeah. What was that mistake?
E tangential 2, sir.
E tangential 1 equal E tangential 2, right?
Yes, sir.
And D normal 1 equal D normal 2.
D normal 2.
Right? So here we are now. We are looking at the magnetic boundary condition. Okay? So, reading from what's on your screen, the condition for magnetic field exists at the boundary of the two media. And when the magnetic field passes from one medium to the other, are called the boundary condition for the magnetic field, or simply magnetic boundary condition. When we consider magnetic boundary condition, the condition of the B field and the H field are studied at the boundary. This is similar to the E field and the D field for electrostatics, right? The boundary between the two different magnetic medium is considered. To study condition of B and H at the boundary, both vectors are resolved into tangential to the boundary and normal to the boundary. Exactly like the electrostatic field. So, consider the boundary between two isotropic, homogeneous, linear material with different permeabilities, mu1 and mu2, just like epsilon 1 and epsilon 2. So let us look at it here now. Medium 1 with mu1, medium 2 with mu2. And we have gone through the shrinking of these delta volume and these delta area already. We resolve the B field into the tangential field and the normal field. That's tangential to the boundary, normal to the boundary. Similar thing here for the H field, H normal, H tangential. This is your vector, your vector that you're resolving into the normal tangential component. Okay. So as we go along, we will be drawing reference to this, and we will be drawing, which we already labor on in details for the E field already, right? So we will be drawing reference to this, and we will be drawing reference to the E field. Okay. Gauss law for a magnetic field. The integral over the closed surface of B dot ds is 0. So, B dot ds here's your ds. Your ds is top, bottom, and the sides going around. So these are the three. B dot ds is 0. So the integral B dot ds for the top plus B dot ds for the bottom plus B dot ds going around is equal to 0. So what did we do before? We shrink this. We shrink our delta H. So our delta H now becomes, it approaches right here for the top and right here for the bottom. So this shrink. So we say, as delta H go to 0, the cylinder tends to boundary and only top and surface contribute to the surface integral. So as we shrink this to 0, the height here is literally 0. So you would say, boy, you really don't have any surface on the side. Right? Follow me so far?
Yes, sir.
So as we are very much interested in the boundary condition, reduce delta H to 0. As delta H go to 0, the cylinder tends to boundary, and only top and bottom surface contribute to the surface integral. So then, this go to 0, right? So the surface integral are calculated for top and bottom surface only. These surfaces are very small. Let the magnitude of the normal component be normal to be normal, and be normal 2 in medium 1 and medium 2 respectively. So what this is saying you see, this is a curve, right? Normally, over the curve here, this side, because it's a curve, it's not a straight line. This size would be a little different from this size, right? At the boundary, because it's going like this. It's going like it's going like this. So at the boundary here, this size would be a little different from this size. As a matter of fact, this would be a little bigger, right? However, we are saying that because we should shrink it so close, it's pretty much the same. So top plus bottom equals 0. This is the top, this is the bottom.
So the bones that they're referring to would be the sides.
Hmm?
The bones that they're referring to would be the sides. But they say where the cylinder tends to boundary.
No, man. The boundary, this is your boundary. This is your boundary. Your boundary is this.
Oh, so that is where they say cylinder tends to boundary.
So this is it. This is this, right?
Yes.
So because this is curve, we're saying on this side is a little, the ear on this side is a little bigger than this side. But we are going to approximate it to 0.
Good.
Right?
Yes.
Because of the fact that we do this. B normal 1 is this, and B normal 2 is this. So when you do the math, come all the way down, B normal 1 equal B normal 2.
That's 0.
B normal 1, remember, this is 0. This is 0. So we are left with this and this. So we do a reasoning to say this ds here is the same as this ds here.
Oh, we're left with top and bottom. I thought you were saying top and bottom gonna 0.
No, man.
Okay.
The different, the side gonna 0.
I get it now.
So when you work that down, B normal 1 delta S, because we are saying the top delta S is the same as the bottom delta S, is equal to B normal 2 delta S. So B normal 1 equal B normal 2.
Okay.
Just like how we have E tangential 1 equal E tangential 2. Note, note that for the magnetic field, the H would be like the E in the electrostatic field. So, and the D would be like the B, right? So you see, there is a slight shift there. Now we know that B equal mu H. So mu 1, this, equal mu 2, this. Hence, do the cross multiplication, this obtains. All right? So, that is that. Now let us look at the tangential component. We're going to start with Ampere's law. Ampere says the integral around the closed path of H dot dl equal I, the current enclosed. Going back to here, here's our closed path. So the integral around this path of H dot dl is equal to the current enclosed. So H dot dl, your dl would be from A to B, B to C, C to D, D to A. A to B, B to C. How about this? A to B. Oh. A to B. C.
And use 1.
Then just break this. Your internet connection is unstable. I'll go on that. They just, for reason you will see, instead of going B to C, they go to B to 2 and 2 to C. So A to B, B to 2, B to 2, to C. Yeah.
So once so is it that can't go from B to C, sir? Is it that we can't go from B go straight to C, sir, for the limit?
We're gonna shrink this, So that's the reason why they break it up.
Oh, all right.
But this is what? What is this? B to 1, A to B. Okay. Okay. I'm missing a figure. Anyway, we're going around the thing. We just break it up. From figure 814, that is the one up there. The closed path is placed in such a way that it's 2 A to B and E to D that are parallel. to the tangential direction of the surface, which while other two sides are normal. So A to B and C to D are tangential. These two sides are normal. The closed part is placed in such a way that half of its portion is in medium 1 and the remaining is in medium 2. You understand that? Half is in medium, half is in medium 2. Now we are going to shrink it. So we have the normal component, shrink it down to 0. Right? So assume K is the surface current, normal to the path. So we are saying the current around the way and that way. It is in opposite direction from medium 1 to medium 2. There are we again. Okay. So the current is opposite. Right? So K D current times the width H dot DL. This delta H, we shrink it. So this is not, these two are going to go to 0. Because like we did before, bring this down and this up. So right there, the delta H, come on. Your delta H is approaching 0. Right? So this gone to 0, this gone to 0. This is in the opposite direction of this, so it's minus. Right? So that comes down to H tangential and here is the same, so you can drop those out, equal K. So this obtains H is B over mu. B over mu. So we are going to consider a case where there is no surface current, K is 0. Right? So that gives you this. H tangential equal H tangential 2. And your tangential component of B is equal to this. Okay. This is a very significant statement. From these two equations, this one and this one, H tangential 1 equal H tangential 2. So your H component in both medium are continuous. Right? While your B tangential component is equal to something, so it's discontinuous. Right? B component is discontinuous. These just follow logically. So, see if I can find
Link. There's some upstairs. I have to restart before I start.
huh?
Yeah.
Okay.
Yes, sir.
All right. While you're doing that, I'm going to try and find an example.
All right.
Hello?
Yes, sir. There.
Yes, sir.
All right. So here's the story now. The XY plane I'll go on as well.
1. Lecture notes. (2018 to 2019 2B) Tech I semester, CREC, R17. Mr. Kondragunta Jagadish Babu, Assistant Professor. Chattalawada Ramnamma Engineering College, Autonomous, Chattalawada Nagar, Reneganta Road, Tirupati, 517-506 Department of Electrical and Electronics Engineering. 2. Syllabus. Unit, IELECTROS.
Getting it back?
Yes, sir.
All right, good. So, all right, now, hear this one now. The XY plane serve just write it down. XY plane serve as the interface between two. You have that?
Sir, when I get from between, where's the upper between?
The XY plane serves as the interface between two different media.
Okay.
Medium one, which is Z less than 0, is filled with a material whose mu r equals 6. And medium 2 which is Z
Medium 2, which is that what, sir?
greater than 0, is filled with a material whose mu r equals 4. if the interface carries current one upon mu naught AY milliamp per meter, and B2 equal 5 AX plus 8 AZ milliweber per meter square. Find H1 and B1. All right, read back to me what you have. Let me make sure.
All right. The XY plane serves as interface between two different mediums. Medium 1, which is Z less than 0, is filled with a material whose mu R equals 6. And medium 2, which is Z greater than 0, is filled with a material whose mu R equals 4. If the interface carries a current 1 over mu naught EY milliamps per meter, and B2 equal 5 AX plus 8 AZ milliweber per meter squared. Find H1 and B1.
All right, do that for me. The first one who do it have extra credit. Now that take too long because we have I'm gonna see how much time I need to finish. I'm gonna finish. All right. Then we can run through what we have in a half hour. So take 15 minutes to do it.
We can just do that one already, sir.
Hmm?
We can just do that one already, take up less time.
Think about what I do. We have to do. What do we do? But me I said try something first. You know, I want to try nothing. I'm not so lazy. All right, you there?
Yes, sir.
First thing, no, is that what is B2? B2 was given, right?
Yes, sir. That's 5AX plus 8AZ.
So B2 equal 5AX plus what? 8.
8AZ.
Sir, you're recording this video? You look like you're recording it, you know.
What do you mean? You just have to figure that out.
Just I see it.
What's the record, man? If we go back up here, where's that again? What's B1 now, man? Where did we do the normal component? B1 normal. Okay. So if we go here, right? We said B1 normal equal B2 normal, right?
Yes, sir.
So So come back here now. B2 is 5AX plus 8AZ. So we can say B1 equal B2. And what is that equal? What's the normal component? What's the normal component? This is a picture of the problem. So your normal component is in the...
Maybe the 8 AZ, sir.
So it would be the 8 AZ. All right? Equal what? So what is H2?
I was thinking,
You have B2. So what is H2?
B2. Yeah, B2 over mu 1 over mu 2, sir.
Right? Which is equal over 4 mu naught times that. Right?
Yes, sir.
So what's H1?
H1 over mu 1.
What's that equal to?
6, sorry, 1 over 6. So it'll be the same vector as B2, sir. So B1 be equal to B2. Asking, sir. Asking if B1 is equal to B2, sir.
No, that we say over here. No.
Yes, sir.
B1. What's B1? We don't know, right?
No, sir.
Okay. Now, this is the only little trick I put into this one. We said that H1 shall equal H2 tangential, right?
Yes, sir.
Correct?
Yes, sir.
Why did we say that again? Try to remember, we just said half an hour ago. Why did we say that? We said that because, let me go back up here. We said surface current right here, right? So K is 0. And that gave us this, which is this. Now, if we go back to the problem, what did we say about the current? The problem says the interface carries current of 1 upon mu naught AY. Not true.
Yes, sir.
So H1 tangential don't necessarily equal H2 tangential. In fact, H1 minus R 1 upon 6 mu naught times. We're just gonna put in a placeholder dx ax plus.
Hold on. Sorry, Star. So we know you know.
Look how long we start back.
No, this.
Me see a thing I come up here. Connection is weak. So I don't know. Everybody getting it?
You know, so many I want to go to the question like you know. I never realized they'll come back. Which one is that?
Fix up that language and go back. So me
What is
follow.
that?
Fix up that language, man. Fix up your argument. How do you mean me come back? Eh?
You find B1 already?
I'll go forward to it. I'll go forward to it. Oh, back. Don't come on here, Reggie.
Alright, man.
Is it?
All different formula I use.
And a different father. So show you what I want.
I use H1 or something.
You miss what I said?
Yeah.
Tangential. Just catch this down so. Alright. Just catch it down so. Plus. 1 upon AY. Alright. Remember. Copy this. I say H1 tangential equal H2 tangential. Remember we said it was a special case when we don't have any surface current. Right?
Yes, sir.
If we go back up here, so again, away there again. A special case where the boundary is free of current. So this case, you see the internet connection is unstable. You see that?
No, sir. Easy alone can see, sir.
Because you're unstable right now.
So if it's free of current, that means K is 0. But in the problem that we is equal to 1 upon mu naught A. So K is not 0. So we have to revert to
That formula.
yeah, which work out to this. Which is just a minor thing.
First,
So we can equate this. We can equate this with, so we say that would be equal to
sir, there's a K stand for the current.
surface current.
So the 1 over mu naught AYR. Not a current as well?
That is the surface current K.
Why you have it in the equation 2 times?
Huh?
Why you have it in the equation 2 times?
Where?
In the equation we write K, H1 minus H2 times AN. So you have K that's of
This?
the last term that I equation.
Right.
1 over mu naught AY. So that's
Right.
correct.
Because we revert to this. So what we do is just, we say this amount to H1 cross AN minus H2 cross AN equal K. So we bring over H2 cross AN on this side. Right?
Transposition.
K. This is the K.
Okay.
So H1, we equate it cross AN. Plus what? Plus this. Which is this. So from that now, we know that by is at 0, because this is what we're trying to solve for. You know? So by at 0. as we complete, as we go around, VM keep changing. So when you go around one time and come back to the same point, VM is not the same. Remember, C equals 0. Integral E dot dl equals 0. The internet connection and still with me?
Yes, sir.
Steady magnetic field, del cross H equals Jx is 0. Integral H dot dl equal I. These are all equations that we have developed. Right? All of this is just math. Vector identity. So, okay. This is pretty much a revision. And follow this vector algebra. Follow this vector algebra in the recording. Is okay. Okay. The voltage for the volume charge density. You recall, we developed the integral over the volume of this times that will be the voltage. So all we are doing here is write the magnet. Okay, this is the electrostatic vector potential. When we do the comparison with the magnetic field, your so this in your electrostatic equivalent to this in your magnetic. Right? So your magnets, this, work out to this. I want you to go through slowly. All it is math, but what I will be happy with is that you take away from the class what I'm going to tell you next, which is about inductor and so on and so forth. Right? But to really appreciate it, I want you to understand. And by the way, if you guys want available, I can give you one of the makeup. Do you want it?
Again, sir?
Yes, sir.
If you're available, I can give you a makeup class next week, Tuesday. Are you good?
So when I test her,
We soon talk about that one.
we are gonna do another assignment.
If you come to class on time, you know, man.
Eh?
If you come to class on time, you know, you'd get all of them information, but me soon give you again. Me soon go over that information again. Wait till we finish this.
All right, sir.
Okay. So let me now run through what me really want you to take away. As I'm telling you. Yes, ma'am. All right, I'm in class. I'll call you back. Mm-hmm. Mm-hmm. Okay. So, inductance and capacitance. I show you already, we got your resistance, we got your capacitance, now we are got your inductance. And all them are people that know about it too. Are the three familiar parameters with circuit theory. So, let me tell you, you will know what Professor Isaacs I tell you. Because you might know that we have already discussed the parallel resistance chapter. In this section, we discuss about before that. If a coil N with N closely wound turns around where a current I produces a flux phi, and the flux linkage links or encircle each of the N turns, the flux linkage gamma is defined as gamma equal N phi. You know that from networks, right? Maybe them not use the same. Maybe they use another character for this, you know. But the flux linkage equal the number of turns times the flux. So L, which is your inductance, equal N phi, that is the number of turns times current. You remember that from networks? Guess not. So see it here. Surface 1, surface 2, flux, linkage, link between this turn and this turn. The flux of circuit due to the linkage of circuit 1 is given by B1 DS2, right? The flux on circuit 2 due to the linkage from circuit 1 is given by this. So this is a common networks problem. Inductance per unit length of a very long solenoid. See a solenoid there? So a solenoid have n turns per unit length carrying a current I. So your B field is given by this. Flux given by that. Flux inductance is this.
Sir, is that an A for the flux linkage?
No, it's a thing like this. Not a A.
Okay. Okay.
All right, let us assume the current is uniformly distributed in the inner conductor so that inside the inner conductor, we saw something. And I saw part of the problem here. Anyway. So you have you're familiar with no electronics. You're familiar with like this. Right? So how they make that? You have the toroid, which have a certain mu. What you're interested in is inductance, L, right? And the current that you're putting in, you can determine the flux. And hence you can determine the inductance. The S is a cross section of the, you determine what the current is. You know what the mu is, it turns. So you can build one of this to give you the inductance what you want. All right. So energy, I think this is where you would start from in network.
Yes, sir.
Not true?
Yes, sir.
Right, so LDIDT, what's that again? What's LDIDT?
I remember I took it, sir. Remember, then we have to do the voltage, sir. Yes, sir. See have it there, sir. So V equal LDI dt.
Right. Voltage drop. So that's about it. All right. So that's it. We start from here. We're going back over the whole thing again, but in time varying field instead of static field. Some of you guys should really consider doing, look at transformer and all of those things. All right. So that's about the course now. So I want to say I want to know, you know.
All right, so we were to, well, we already started, we're getting the assignment this evening, I say, and to be submitted next week, Thursday.
All right.
Submitted in the same manner as we submitted the first one, right?
All right.
And then the exam.
Hold on. Ma'am, I will send the problem set to Ms. Dunkley this evening. So if you don't have it in your, on your in your email by tomorrow morning, you call her.
All right, sir.
All right.
Okay.
Sir.
All right, sir. Like what is the assignment? Why don't you just give it to Jerry and Jerry will send it to me?
You're not gonna send it to Jerry too.
All right.
So contact us.
Sir.
It's don't play. You probably know all our email, we don't know.
I send it to Jerry. But by the way, I don't know. I think I'm 49. Everybody get them grade?
What's up?
Sir.
The test?
Yeah.
Yes, sir.
Yes, sir.
Sir.
Yeah.
I didn't get mine, you know. Because I did my test at work, and when I came back and I put on a log like I was supposed to log out, checking over everything, it was at the time, the deadline pretty much, because I had to run back to log out, and I didn't see the grade posted. I sent an email to Dr. Isaacs as well as Mr. Dunkley. So I don't know if they told you about this. Sir?
Yeah, what are they? What are they? I'm gonna check something.
Yes,
How much time we have left? Let me know on the time.
6 minutes.
But you are over the entire thing, but it push on the miracle line. So what we done here is this point just about what is
Right. Not here yet.
this
Yes. Mine under other application, database, dietitian, organize, client manager.
I hope we attack our Shane.
Sir? You mean me, sir?
Yeah, are you
No, Rainbird, sir.
last name of Rainford?
Yes, doctor.
Rainford. It's a 50 name. I don't see a Rainford. Biggest Blackwood, that Clark. Hamilton. Nothing no Rainford in this list, sir. I don't see a Rainford, sir. You sure you pay?
Yes, sir. Through SLB, sir, and everything, because I started this year, so everything was covered.
I don't see a Rainford on this list, so maybe that's that's the cause of the problem.
Okay.
The only arm I see Ramsey, you there, Ocean? I see Ready. I see Reed, Rose, Royal, I don't see no Rainford.
All right, sir. So I've talked to Miss Dunkley then to see what the position is, because I was everything was sent through on the system, and I registered and everything for the second semester.
Yeah, that out of my hand. Maybe that's why.
Also, sir, you never did get the test that we did then, sir. That means you never see my name then, Judge, sir.
Pardon me?
That we had submitted, sir, the assignment.
I don't have nothing to do with it. I look at the grades them for the test, so we just
Yeah, okay, I understand what you're saying, sir. I understand, Dr. Watt. I understand.
So check with Miss Dunkley why you're not on this list, because
I will do so. Thanks, sir. I will do that.
all right.
Thank you, sir.
Yeah. No, the test date. What we agree on again?
Monday definitely outside.
it was between Sunday and Monday, but a man say have a match test Monday, sir.
You see what I mean?
Two test Monday, sir. Monday outside, sir.
All right. We could come to the consensus, sir. Exam really done the 10th.
10th hour.
But hold on, sir. If everybody willing to do the test on the 11th, since nobody now want to do it Sunday, And the 7-day man, them have a complaint say a Saturday. If everybody willing to do it the 11th, which is a Tuesday, then we can do it Tuesday because nobody is supposed to have no test.
Yeah.
But in the day or in the night, in the evening, we'll go home.
But remember say university said the 10th. So we can go over that.
That's a good point. That's a good point.
University said the 10th, but I think it will be up to the lecturer.
Okay.
So I don't. There were persons who had a problem with the Saturday evening after the sun go down, like in the evening, like 7, 8 o'clock, and the sun.
Yeah, but you still have to remember say some people have 2 tests Monday.
No. I mean, no, man. I don't mean not next week. You know, I mean
Saturday
the week
evening?
after. Right. The Saturday of the
The Sabbath man, them went on the class. We need to speak up.
Saturday after when?
after sundown, because Sabbath is normally from Friday to sundown.
Let me use date. Let me use date. Which date are you talking?
It's the 8th. I think that would have been the 8th.
That is correct, my brother. That is correct.
I'm talking about the 8th. No, but what I'm saying is
August.
Well, yeah, but what I'm saying is, brother, I'm gonna have 2 tests Monday.
Yes, a Monday outside.
Which Monday?
The 10th.
The 10th
No,
outside.
I will listen.
So
Listen, listen on. What I'm saying is, I'm gonna have 2 tests Monday. That means that if you go to the exam, the 8th, I'm gonna set up 3 tests.
You never give you a date, you know, you said dates, we never know, said next week, the week after Monday, without the